Hello, this is Mr. Win, and this video is about vectors. So quick introduction for vectors. If we have force or velocities, a single number can't explain everything. We have to know the number, the magnitude, like the length, and the direction, like the angle. And if they have the slope, you can kind of find the angle from that. Alright, so we use what we call directed line segments. In figure 6.15 right here, we have a directed line segment PQ. P is initial or starting point, Q is the terminal or ending point. The magnitude has a symbol, I'll say double absolute value of PQ, we just call it magnitude, and we just use that distance formula to find that. Also, two directed line segments are the same or equal if they're the same magnitude and direction. So in figure 6.16, all these directed line segments are the same. They're the same length and they're the same angle or direction. These are also called vectors, and we write vectors using lowercase letters in bold. So let's try a problem. Let vector u be represented by the directed line segment from p at 0, 0 to q at 3, 2. And let vector v be represented by the directed line segment from r, 1, 2 to s, 4, 4. So show that those two vectors are the same. So notice on our regular coordinate plane, here's p to q, here's r to s. All you have to do is show that they're the same angle and same length. So to find the magnitude, use the distance formula. So d equals square root x2 minus x1 squared plus y2 minus y1 squared. So they're both square root of 13. And then figure out their angle. They just found the slope. They both slope up 2 over 3, up 2 over 3. Alright, so they are the same thing. Alright, component form is very, very important. Component form is a vector who starts at the origin. And we're going to move everything to origin because remember, location doesn't matter, only the size and direction. So we're going to call component vectors, component form of vector, standard position. Again, it starts with 0, 0, the origin, and then its endpoint will be v1, v2. So we can say vector v is, we use these arrows. So instead of parentheses, look like kind of pointed, a weird, I guess, less than and greater than sign. Alright, so they call the v1, v2 part the component of v. And if v ends at the origin, that means it's a zero vector because it doesn't go anywhere. In general, when you have any 2 points and the vector is connecting them, you just subtract the x's, find how long the x part is, find how long the y part is, and then basically transfer that into the standard position, starting position, origin, and just get a v1, v2. And to find the magnitude or length, just instead of doing the distance formula, you can just square the two components, add them together, then square root that. So this is a little faster. And if it's equal to 1, that's the unit vector. And if it's equal to 0, that's the 0 vector. Alright, two vectors u and v are equal if u1 equals v1 and u2 equals v2. So from example 1, we had this. If we do 3 minus 0, that's 3. 2 minus 0 is 2. And then we tried for v. 4 minus 1 was 3. 4 minus 2 is 2. Again, they're both the same. 3, 2, 3, 2. X component 3, x component 3, y component 2, y component 2. Alright, finding component form of vector. So here they have 2 points. So first, we're going to subtract, find how far the x's go and the y's go. So they did q1 minus p1, where q is the terminal point, that's why I went first. So negative 1 minus 4 is negative 5. Then q2 minus p2, so 5 minus negative 7, that's right, adding. So that's 12. So here's the picture, but we could actually have it from 0, 0 going to negative 5, positive 12. It would be the same distance. I wish they drew that picture up, but that's right. Alright, so now we know what v is, the component form. So you want to find the magnitude or how long it is. You just do distance form is 13. So this is actually 13 units long. Alright, vector operations. There are 2 things we can do. We have scalar multiplication and vector addition. Scalar multiplication is very easy. That just multiply a constant number. It's basically a dilation. You just multiply that number times the original scalar. If it's positive, it's bigger. So example, half of v would be this. Again, location doesn't matter, just how long is it. Magnitude is half the length, and this direction stays the same. If k is a negative though, it changes directions. So although here's 2 times v and goes to the same, direction the same, here negative v is the same length, but now it's going backwards, and here's negative 3 over 2v. Then we have vector addition. Vector addition is when you add two vectors, you join them. The end of one connects with the beginning of another. So we usually say at the end of one, the head starts the tail of another. Let's say head to tail. So if I have u right here, I want to add u and v, I could just move v up here. So the beginning of v, the tail of v goes here at the end of the head of u. And then once you have that, that's what I have right here, you just go from the beginning to the end to get your resultant, or the real vector. Alright, if you have a negative, you can just, that's a scalar, you just multiply negative 1, it just multiplies these by negative 1. And if you use subtraction, that's adding the negative. So it's going to be basically subtracting. So here, if I was doing a u plus v, here's u and v, but I'm doing u plus negative v, I just do head to tail. So the head of u gets connected with the tail of negative v. So really, from beginning to end, we go this way. Alright, here's some examples. So here's vector v, here's vector w, solve each. These are both component form. So this is find double v. Well, that's easy, just multiply each piece by 2, so you get negative 410. Here's the picture. So from 0, 0 to negative 2, 5, it's 0, 0 to negative 410. It's double the length. W minus v, that's easy, you just fill it out. Do the first part of each, subtract them. The second part of each, subtract them. 4 minus 5 is negative 1. Here's a sketch of the picture. And the last one, v plus 2 times w. You double w first, then you add the first parts of each and the second parts of each. And here's a picture of that. Alright. All the regular rules of algebra still apply. You can switch the order, add 0 doesn't change it, all that stuff. And then we have unit vectors. Unit vectors are where the vector is exactly 1 unit long. We can get that every time by just dividing the entire thing by its length. So if we have something that's, say, 15 units long, if I divide that by 15, I now make it 1 unit long. So you can always get it by dividing the vector v by its magnitude. So we say this unit vector in the direction of v. Alright, so let's find a unit vector. Here's an example. So v is at negative 2, 5. Find its unit vector. So if it's negative 2, 5, we're going to first find how long it is. So we're going to square the x, square the y, square root. So we found a square root of 29 long. So if the whole thing is square root of 29 long, we're just going to divide each component, the x and the y, by square root of 29. Then once you have these two numbers, that's your answer. And we're going to check. We're going to square both, add them together, square root, that is 1. That's good. Alright, we have two standard unit vectors, 1, 0, and 0, 1. That is I and j, just like in this figure 25. We use the bold lowercase I, not the italicized lowercase I for imaginary. But any vector in component form can be put into vector form. All you do is just get each piece separate and have it with I. So remember, v1 and v2 are the scalars, the magnitudes, while I and j are the directions. I is just basically to the right, the x-axis direction, and then j is the y-axis direction. Horizontal and vertical components. Alright, and then when you put in this form, it's called a linear combination of the vectors I and j, because this uses vectors I and j and no other vectors. And any vector in the plane, coordinate plane, can be written as a linear combination of the standard vectors I and j, because everything's in the x-y axis. Alright, so here we're going to try an example. Let u be a vector with that initial point and that terminal point. Write u as a linear combination of the standard unit vectors I and j. So first we're going to turn it to a component. We actually want it at 0, 0. So we're going to do change in x's, change in y's using the terminal point first. Once you have component form, just break it apart, add the I to the x part, add the j to the y part. That's it. Alright, here's another vector operation. You have u and v, find 2u minus 3v. You could turn this into component form, but you don't have to. You can just leave it in this vector form, because it's the same. Just distribute, combine like terms, see your answer. If you want this component form, it'd be -12, comma 19 in those sharper parentheses, also called angle brackets. There's the name. All right, direction angles. If you use a unit vector and theta is the angle measured clockwise, you can say vector u is component form xy, which you say is cosine of theta, sine of theta. This reminds you of the unit circle. And the x part is cosine of this angle, the y part is the sine of that angle. And you can also change it into vector form using the linear combination. So this x part with the I vector, and then the y part sine theta with the j unit vector. All right, you could write it out however you want, and you can basically say to get the angle, you just do the b over a. So you could say it's the y part over the x part, and then you can do an inverse tan to find the angle if you wanted. So let's try some problems. So find the direction angle of each vector. So for problem A, 3i plus 3j. So we're going to right 3, up 3. Here's our line. What's this angle? Well, tangent of theta of this angle is b over a, so it's 3 over 3, y over x. Inverse, or you should not see unit circle. If it's the same, that's 45 degrees. Here, if you want to do 3i minus 4j, it's down here. You can use the reference angle idea. You draw this triangle. You notice it is arctan -4 over 3. You use a calculator for 53 degrees, but we want the standard angle, so we can subtract from 360 to get this 306.87 degrees. Alright, you can use vectors anytime a trig is necessary. For this word problem, it says it's 30-degree angle. If you have a 30, 60, 90 triangle, you know the pattern, so this is 100. That's across the 90, you know across 30 is 50, and then this is 50 root 3, but they forget those. And then they find the magnitude. They check the magnitude is 100, but that's one way of doing it. You could use this. You can use solve more complicated problems. Here's a picture. A force 600 pounds required to pull a boat up a diagonal ramp, 15 degrees from horizontal. Find the weight of the boat and trailer. So hope y'all know gravity is a downward force. This BC is the normal force against the ramp. And AC is the force using go diagonal. This way is parallel. By construction, these two triangles are similar. So if angle ABC is 15 degrees, and then here you can do sine, this right triangle. So sine of 15 is O over H. So AC over BA, which we're trying to find. We nail AC is 600, so we have sine 15 equals 600 over the magnitude, how long the direction of BA. Multiply both sides by BH, get rid of the denominator, divide by sine 15, type in the calculator, 2318 pounds. Alright, but the best case is this. Those bearing problems we did before, we can use vectors. This will get the same answers as before, but we'll avoid using the law of cosines to find the magnitude, and we'll avoid using law of sines and adding and subtracting to find the bearings. So here, an airplane goes through a bearing of 330. So 330 is this. This is 30 degrees. Now they did 90 plus 30 is 120 because they want the standard angle. They found the x and y components of this vector, v1. Then for the wind, pushing this way because it has a new vector, they found the x and y components for the wind vector. And all you do is add two vectors together. Remember, the end of one goes to the beginning of the head to tail. So this true v, this final v is our true magnitude. And then we'll find our true bearing in a second. So when you just add the x's and the y squared, you get this. Here's our component for this final vector, the resultant vector. To find magnitude, you just do distance formula. So you square the first thing, square the second thing, add them, square root, you get 522.5. Then to find the angle, you can just do tangent theta equals b over a. So the y part over the x part. So tangent theta is this, arctan both sides, get that. Then you have to do a 180 minus this to get your true bearing. And that's it. Hope you enjoyed the video. Make sure you ask questions. This is a lot taken, so make sure you take good notes and really come to live sessions. Alright, thanks for watching. Bye.